Today we're happy to have Peter Fiebig from University of Erlangen-Nuremberg and the IAS, and he will be telling us about Lefschetz operators, Hodge-Riemann forms, and representations.
Well, thank you very much, Maki, for the kind introduction, and thanks a lot to the organizers. Well, you see my title here, Lefschetz operators, Hodge-Riemann forms, and representations. But I should say right away that I'm mainly talking about representations and some analogs of Lefschetz operators and Hodge-Riemann forms that might be helpful in representation theory. So I want to start with some motivation. Hard Lefschetz. So if you have a compact Kähler manifold, complex compact manifold that comes with a Kähler form, then this Kähler form gives you a morphism of degree 2 on a cohomology. And so the Hard-Lefschetz theorem tells you that for all k bigger to 0, the kth power of this operator L gives an isomorphism between the n minus kth cohomology and the n plus kth cohomology, where n is the complex dimension of the manifold or half the real dimension. So this gives you this very nice symmetry between the cohomology groups, but also a map that factors over all the cohomologies in between. So that's the Hard-Lefschetz theorem. And the nice thing that links this to representations is that you can reformulate it in the following way. So you can also say that this cohomology, you have to shift the degree a little, is a Z-graded representations of SL2, such that, for example, this upper triangular matrix acts as the operator L. And so the Z-grading, if you shift it correctly, gives you the action of a generator of the diagonal matrices. Well, what I wanted to say here is that this Hard-Lefschetz theorem is of, I think, utmost importance, or analogs of this theorem are of utmost importance in representation theory. They are very often connected to decompositions of certain structures. For example, it's a very important ingredient in the proof of Ben Elias and Jordi Williamson of the Cauchy-Lussig conjectures in a framework of circle bimodules. There you have a statement like this, where you have to prove that a certain operator between certain graded vector spaces just behaves like this Lefschetz operator. So this occurs very often in one guise or the other in representation theory. I want to give another example that we all know very well, that has a kind of very similar structure, even though it's a very different theorem, namely the geometric Satake equivalence. So we talked a lot about this in the seminar, of course. So I will be very brief. So let me, start with the Langlands rule group. So I define the affine Grassmannian over the complex numbers. And then for every weight, we have this toric fixed point in the affine Grassmannian. And we have this Iwasawa decomposition that decomposes the affine Grassmannian into semi-infinite orbits. So they are parameterized by the weight lattice. So we have this decomposition. It's kind of from a geometric viewpoint, it's a little exotic, this decomposition, but for the cohomology of for the hypercohomology of perverse sheaves, this is a very important decomposition. Namely, it leads to the weight functors and the weight decomposition. So if you have a perverse sheaf F a spherical perverse sheaf on the affine Grassmannian with coefficients, say in a field K, then you get this decomposition of the cohomology by the weight lattice. If you have this these restrictions, contact restrictions to these semi-infinite orbits, and then you take this kind of degree in the cohomology, and you prove, it's not a very difficult proof, you prove that that the cohomology actually decomposes. So the cohomology is here not only Z-graded, but it's actually graded by the weight lattice. So another ingredient is the determinant line bundle that gives you an action of degree 2 on this cohomology of these sheaves. So I remember we talked in a discussion quite a lot about the action of the cohomology of the affine Grassmannian on these hypercohomologies of perverse sheaves, and that they come from the action of the universal enveloping algebra of the centralizer of a regular nilpotent element. And this kind of generates this action. So what I want to stress here is that we have this element on the affine that acts on these cohomologies, and we can use the weight decomposition to decompose this operator. So you can write this operator L as a sum over the simple roots L alpha, because this operator, it maps the weight mu to the weight mu plus alpha. So these are these components come from the weight decomposition that we had on a previous slide. And so the weight decomposition of the cohomology gives you a way to decompose this operator in a direct sum of these L alphas. So we have kind of a similar situation. So we have a graded space and an operator of degree 2 or degree alpha here now that acts on the space. So here you see a picture that should illustrate this idea. So the Z grading of the cohomology gets refined by the weight decomposition, and you get these operators here. So these operators, these operators here, this could be the operator L alpha acting on this weight space here, and this is L beta, and you have another component of L beta and L alpha. So the geometric Satake equivalence now is a statement that is much stronger than what I'm saying here, but it implies that there is a structure of a GK module where GK used to construct the affine Grassmannian with over K. So this acts on this hypercohomology, so such that these L alpha components of this operator L correspond to these Serre generators of the Lie algebra GK. So this for all so simple. Okay. So the motivating question for this talk is now, well, what we say, I mean, if we look at these two examples, if we have a graded space together with operators of degree minus alpha, if you, well, you see here, I switch from positive to negative roots because I will mainly talk about representations, and I think of high representation KBO. So here, these L alphas, you see they were kind of corresponding to positive roots if you want. But here we want these negative roots. So if we have a graded space M, X graded, and we have these operators, when does that actually produce a representation of the linear algebra? So if these operators give you a representation of the linear algebra, it's actually unique. Because, well, you already see that in the directions where you have a hard Lefschetz. So if you have an operator of degree 2, way to make it into a representation of SL2. But what is the additional structure that we need to make a datum like this into a representation? Okay, so let me just review the setup. So we have this graded space. Let's, for the moment, say it's a K vector space. K is at the moment an arbitrary field. Let's assume, just to make the exposition easier, it's finite dimensional. It's not necessary. You can suppose that the weights are restricted from above or something. And suppose that for any simple root, we have an operator of degree minus alpha. Okay. Before I something is it only on my computer so very slow if I switch the slides? Anyways. Before I if I give some definition, I have to give some definitions first. So
Peter,
yeah.
sorry if I can. Yeah,
Is there a question?
The sound is lagging sometimes. So far, I think it's not been so much that we can't follow anything. Yeah. But yeah, if it starts to become a problem, I'll let you know, and we might have to reconnect or something. So,
is it better now? Do you hear me?
Yes, I hear you.
Yeah. So I again was connected with the computer to the wrong wireless.
Okay. Yeah. No worries. Let's see if this is better.
Okay. So let me give you first a definition that we need in a second. So a subset of the weight lattice, I want to call it closed if it has the following property. So if we have an element in this subset and a simple root, then also their sum is in this subset. So the closed subsets, they are kind of closed by, you know, well, they are open to plus infinity in a sense. This actually gives you topology on X, but we don't really need that. And if you have such a closed subset, you can define a subspace in our graded space M. So I call it M sub I. And this is the smallest subvector space that contains all these weight spaces M mu for mu in I. But it's also F stable for all alpha and pi. Okay, so everything that you obtain by these lowering operators F alpha from something closed closed above. So that's the definition. And so the ingredient that you need to produce a representation is actually bilinear form. That I call an HR form for Hodge-Riemann because it kind of reminds you of the Hodge-Riemann form in the hard Lefschetz setup. So what is that? So this bilinear form is, well, it's a bilinear form on M. So there's the some conditions. So it's first, it's symmetric and non-degenerate. Okay. Then it's weight spaces are mutually orthogonal. Okay. So these operators F alpha, they have adjoints. I call them F alpha star and F beta star. And now there's an SL2 condition here. So the operator F alpha should commute with the adjoint of F beta if alpha is not equal to beta. And it should act, diagonalizably on the, so this commutator acts diagonalizably on this graded space. So the eigenvalue is mu alpha check if alpha is beta. So that's just an SL2 relation. So
can I ask you, Peter?
Sure.
Is that the same as asking to have a representation of G? What is missing?
So at the moment, so it's not clear that you get the Serre relations out of this.
If the representation is integrable, the Serre relations follow.
If you have this bilinear form, yes.
No, even without the bilinear form, because that's just a general fact that if you have say E alphas and F alphas, and the E alpha F betas satisfies the relation you put, then you automatically have the Serre relation. So it becomes, for each alpha, you have a representation of SL2, you agree? And then the beta, you look at what the beta is doing, and that's then it's something about representations of the SL2 alpha, and so you deduce. I think it's explicitly stated in Chris Ginsburg. So that's not true, of course, on things like Fermat modules or whatever. I mean, you need a finite dimensional representation of. You need to use finite dimensional representation theory of SL2 to make that work. So you need integrability. But that's a consequence. Serre relations are a consequence of those.
So you're saying that if you have SL2 representations in every direction and these operators commute, then you already have a representation of the Lie algebra.
Yes, if the SL2 representation is locally finite, yes. Some of finite dimensional, yes.
Okay. Okay, I didn't know that actually.
I know, but it should be more widely known. Yes.
Okay. Well, I have more to say actually than this, but thank you. I will Chris Ginsburg. I will check that.
I look for the precise reference and put it in the chat. And yeah.
Okay.
And see that Jordi is confirming that. So that's good.
Okay. Sorry, I didn't know that. Okay. So so what I wanted to say now, I mean, I will generalize this in a bit. Let me just go on with this this bilinear form. So so you have these commutation relations, okay, and I also want that for a closed subset, the restriction of this bilinear form to the subspace is also non-degenerate. Then there comes the theorem. The existence of such a bilinear form with these properties is equivalent to the existence of a structure of a semi-simple X-graded representation of GK. By the way, Raphael, is that in any characteristic, or are you talking about characteristic 0? Well, I checked the reference. So here the characteristic should not be 2. So the existence of this Hodge-Riemann form is equivalent to the existence of a structure of a semi-simple X-graded representations on M, such that these F alphas are just correspond to the CR generators. Okay. So there's also a group version. I put group in parentheses because I want to talk not about the group, but about the algebra of distributions. So this is the following. So first you take the universal and invariant algebra of the complex Lie algebra corresponding to the root system. And in there you have this constant ring, the constant Z form that is generated by these Serre generators. Take them to the nth power, but then you divide by n factorial. And you do this for all simple roots and all n bigger or equal to 0. You take the ring that's generated by this inside. U of GC, the complex universal enveloping algebra. And now these SL2 relations are kind of replaced by a fancier version. So again, these generators, of course, they commute, but E alpha and F alpha, the nth powers, or these divided powers, they satisfy this kind of relation. This is again an SL2 calculation. And so it's just for a ring R, we define UR to be well, the R version of this integral version of the complex universal envelopment algebra. So for a field K, this is the algebra of distributions of the corresponding group. Okay, and we are looking at UR modules, because if you have an integral X graded UR module, then you have a module for the group. So if you're interested in, so from my point of view in this talk, if you're interested in representations of the group, here we look at the algebra of distributions, and it's a good replacement for the universal enveloping algebra of the Lie algebra. In characteristic P, in positive characteristic. So again, our general setup is this: that you have a graded space M, and now these operators F alpha n, they should correspond to these divided power operators later. And well, you again have to modify the definition. Well, it's not really modified. So you again, for a closed subset I, you define Mi as the smallest submodule of M, containing all these weights, and it's stable under all these operators. So in case R is a field, the definition of the bilinear form that gives you a representation of this algebra of distributions is the following. So again, you look at the bilinear form, which is symmetric and non-degenerate, and mutual weight spaces are mutually orthogonal. And now you replace the SL2 representations by these fancy SL2 representations. So I rewrote them a little. So here's just the same. These operators commute. The star operators are again the adjoints with respect to the bilinear form, and the real SL2 relation is here. Yeah, I mean, yeah, that's just the relation that you ask. And again, you want that for these subspaces corresponding to closed subsets, that the bilinear form is non-degenerate. And then the theorem is again just the same. The existence of an HR form is equivalent to the existence of a structure of an X-graded semi-simple UK module on M. Oh, I think I have to exclude characteristic 2 here. So a semi-simple UK module on M such that these operators are determine the action of these nth divided powers of F alphas. Okay, so this is the group version, but now maybe it gets a little more more interesting if you replace the field by ring, and it should be local. So the p-adic integers, for example. So I don't want any or it's not necessary to complete CP in any case. So this is a real algebraic definition of these p-adic integers. So you take these the subring in Q, A divided by B, where B does not divide B. So again, you have this graded space with this operators f alpha n. But now in the local ring case, there's one additional assumption on this data that is quite important for what I'm going to tell you, is and namely that these subspaces Mi, that these are actually direct summands in the category of CP modules, so that these inclusions split. Again, M is free of finite rank, which is also probably not such an important thing, but yeah, I'll say something a little later on about that. So the definition of an HR form is again the same as before. You have these fancy relations this time, and you assume that the restriction of B to these subspaces is only faithful. It doesn't make sense to ask for non-degeneracy in this local version. You want the restriction to be faithful. And now what you get, again, you get a representation on M, and this time you get tilting modules. So the existence of a bilinear form on this M is equivalent to the existence of an UCP module structure on M. Yeah, maybe I should. So I should have written here if alpha n is this nth divided nth power, and with this structure, M is actually a tilting module. So in this way, you get tilting modules. Maybe now is a good time to stop.
Yeah. Okay, let's take a 5-minute break. We'll meet back at 3:33. So there's some comments in the chat.
Yes, I'm going. So I'm sorry about the connection problems.
No, I think with the.
Now it's great.
Now it's better. Okay.
Yeah, it's much better now. Yeah.
Yeah, sorry, Maki. We talked about this, and I checked my iPad, but not my computer.
No worries at all. I'm glad if it's fixed. So Jody has a question.
Over R is the real. Yeah. Okay. Jody, is that the question you asked in the chat?
Sorry. Yes. So I was just wondering. I mean, it's like if we take the contravariant form on a weight space over the real numbers, I just realized I don't know what its signature is. I should know, but I don't know.
Yeah, yeah, I don't. I know I can. I don't know. I can't tell you. I mean, I don't even know if it's hard to calculate or.
I mean, this is Janssen's contravariant form, no?
Yeah.
So it's reasonably easy to do in many examples, but I don't think so. Ben says it should agree with the signature on the highest weight space, but I don't think that's true.
What's the answer for SL2?
For SL2, certainly. For SL2, it's just all like just one. You know, it's the binomial coefficients. But I think for the adjoint representation of SL3, it's 1 minus 1 on the 0 weight space. I hope I'm not saying something stupid.
But anyway, the weight space are larger, so I don't understand Ben's comment.
Yeah.
Yes, you're right. No, I understand. I didn't speak.
I mean, it's probably on.
Yeah, I don't know.
It would be a kind of add-on to Weil's character formula, I guess. This kind of result. But yeah, I don't know.
And I'm sure someone knew it, and maybe we also knew it in the past, but.
If I remember correctly, I mean, there are explicit thing. I mean, it's you can say explicitly what it is in terms of the. I mean, of the highest weight for a simple representation for compactly group, but it's not. Yeah, I mean, it's not trivial, or I don't remember. I think Goff was looking at forms on foundation of two rational Cherny algebras, and I remember talking with him, and he explained this case of compactly groups, but it's known, I think, and there are explicit descriptions, but not. Yeah, it's not trivial.
But I have a question. If you have something that isn't irreducible, does this HR form already imply some sort of compatibility between the signatures on different highest weight spaces?
So if you have something that's not irreducible but self-dual, or I mean, do you mean?
Yeah, just like say the direct sum of two irreducibles.
Yes.
I mean, I don't see in the HR statement anything resembling what I think about as HR, which also has some sort of compatibility in science between the signature on various different irreducible components.
No, no, I mean, so the let's go back just a second. So so signs are not present in. I mean, so let's see. This is really a I mean, a really semi-simple theory that I'm that I'm explaining here. So yeah, here, look, this is the semi-simplicity statement.
But so if you take a sum of two irreducibles and then rescale the form on one of them, you still get an HR form.
Well, if you rescale it on you mean on the highest weight, or I mean so if you have an irreducible, this form is of course determined by its restriction to the highest weight.
Exactly.
And so you can rescale on each component. You can rescale as much as you like. This doesn't matter.
Okay.
For this definition, is that
that's just what I was double checking.
Yeah.
Okay, I think we can start the second half.
Okay. So I want to present a different take on this, but this is very much work in progress. I mean, I have one article in the archive on this. You can use the previous theorem, these HR forms on these tilting modules, to actually produce an algorithm that produces the tilting module starting from a highest weight by induction on the weights, because this bilinear form is, I mean, the weight spaces are orthogonal. So let me talk a little bit about this algorithm, or what the local structure is if you carry out this algorithm. So I changed the viewpoint a little. So suppose we have actually two sets of operators on this graded spaces of degree minus n alpha and plus n alpha, and assume that they satisfy these fancy SL2 relations. Maybe let's, okay. And then look at the following space. So for weight mu, let's look at the direct sum of the weight spaces that you can reach by going in simple root directions. Alpha is a simple root, n is bigger than 0, and you have this m mu plus n alpha. This I call m delta mu. And now the f and the e operators give you maps between m mu and m delta mu. So f mu is a column vector, e mu is a row vector. That you can produce using all these operators f alpha n and e alpha n. And so now the properties of this HR form that we want, they translate into certain statements about these e mu's and f mu's. So the first one is that e mu restricted to the image and f mu is injective. And the other is well, that the quotient e mu m mu divided by e mu image f mu, this is a torsion module. So we are over the p-adic integers, and the inclusion here is torsion free. So let me give you a kind of a picture of the situation. So so just as a reminder, so we have mu, we have these two maps between these two spaces, m delta mu. So this one is e mu, this one is f mu. And so the e mu restricted to the image of f mu should be injective, and then there's this torsion phenomenon. So you apply e mu to the image of f mu, and you get something like this this green part. And what you obtain in addition, if you take the full image of mu, I mean, what you get on top of that is this yellow part, and this should signify that you get that the quotient is torsion free, so that the image actually splits in the category of ZP modules. So this is a situation that assures that the bilinear form that you can construct by induction is actually an HR form. This gives you an algorithmic construction of the tilting modules, but also it gives you an idea of how to approximate between Weil modules and tilting modules, because the difference between a Weil module and a tilting module is the difference between this image of f mu and the actual mu. So the idea is to filter this yellow part in order to get approximations to tilting modules.
Peter, could you just show what m delta mu is again?
Yeah, of course. So m delta, delta mu, this is just everything you obtain from mu by going upwards in simple root directions. So maybe I have a little time, maybe I can explain this a little better. So, so this is an idea that comes from this inductive procedure. So suppose you want to define the tilting module at the weight mu, and you have already constructed everything above, all the weights above mu. Then so everything you obtain by going in simple root directions you call delta mu, and these f. So that's everything that could possibly land in mu by applying these f operators. So f alpha n is always an operator from mu plus n alpha to mu. Yeah, I haven't said much more than I said before. Let me go on. So there's this idea of defining generations of modular representations that originated from a paper of George Lustig. I heard for the first time I heard this in Berkeley in 2014, I think. George Lustig gave a talk there and defined on a character level generations of simple characters generations of simple characters that kind of converge to the for p big enough and to the character of a simple modular representation. It starts with, I guess, the character of a Weyl module, and yeah. So, and then by George Lustig and Jody Williamson, it was generalized in the framework of tilting modules. And here it is maybe especially important because, as far as I understood, it's driven by the hope that one might be able to define, or at least conjecturally, character formulas for these generations in terms of lower generations. But so far, I think no one really was able to give a conjectural formula for these generations, let alone give them a representation theoretic realization. It's also in a simple case, it's not clear what these characters, these generations of characters should correspond to. So a motivation for this generation idea is if you look at the tilting modules for, say, SL2 over a field of positive characteristic, and using Steinberg's tensor product theorem, you can actually calculate all these multiplicities, the Weyl multiplicities in these tilting modules. So SL2 is the only case where we know all these multiplicities, and it looks kind of like this. So the way you should read this is that a point corresponds to the fact that the so the tilting module with highest weight lambda as the Weyl module with highest weight mu as a subquotient. So in SL2, the multiplicities are always either 0 or 1. And whenever you see a red dot, the multiplicity is 1. So lambda is here determines the line. So for example, this line might be lambda, what is 5, 6, 7, I guess. This means the tilting module with highest weight 7 has the Weyl module with highest weight 7 and the one with highest weight 3 as a subquotient. So these are the multiplicities for the group, but what is also known are the multiplicities for the quantum group at the third root of unity, and they look kind of much easier. They look kind of like this. So same way to read these multiplicities. And so if you go back to the original picture, I guess you get the idea that there's first a fractal-like or an inverse fractal-like structure appearing here, and that you can define generation. So, for example, the zeros generation would be just the while modules. So can you see that, this slight yellow line? That would be the zeros generation. The first generation would be what you get for the quantum group. So you would cut all these legs off. And the second generation would allow legs of length up to 9. So this would be this. And then and so on. And the question is, are there any modules for a group or quantum group or anything like that that have such a behavior? Do we find something that lies in between the quantum group at the third root of unity and the algebraic group over F3? And so I looked at the algorithm and these torsion phenomena that I just explained on the previous slide. And so there's a kind of naive idea that you can look at this torsion part here and filter it by powers of p. But this does not give you the right answer. You see it already in the SL2 case, because they are first generation characters that where you have a p-squared torsion occurring, and they are second generation singularities or characters situations where you only have a p torsion. So that's not the right way to filter this torsion part. So my suggestion would be to quantize this. So the suggestion is to replace the integers by these quantum integers. So the ring of integral Laurent polynomials. The rational by the rationals by the field of rational functions, the quotient field of this C, and in between the p-adic integers by this field in between. So these are Laurent polynomials f over g with integral coefficients with the property that the prime p does not divide g of 1. So g of 1, g, f, and g are elements in this ring. G of 1 is an integer, and p should not divide g of 1. This is kind of a quantum version of the p-adic integers. And now you can run just the same that I said by replacing every integer. I mean, it's kind of the idea, replace the integers by quantum integers in everything that I said before. And there's an advantage that you get actually much more information about the torsion. The reason is that so the generator of the maximal ideal in this ring p-adic integers is of course p, and over p here we have all these p to the lth cyclotomic polynomials sitting. So if you evaluate a p to the lth cyclotomic polynomial at 1, you get p. So p, the maximal ideal, corresponds to very many prime ideals in this ring. And so now you run the theory with integers replaced by quantum integers, and if you occur p torsion, you can actually distinguish if it comes from the p-th cyclotomic polynomial or the p-squared cyclotomic polynomial. They are both irreducible elements. If you have a p-squared torsion, it comes from kind of products of these cyclotomic polynomials. So in this way, if you look at distortions, you have a way to define approximations of tilting modules. It's a little technical, so I haven't put this in my slides. Yeah, for the reason that it's a little technical, and it gives you a kind of intermediate tilting module for any subset of the natural numbers. So you can just look at tau I torsions where you at the situations where you find tau I torsions for I being coming from a certain subset of the natural numbers. But there are several problems or questions that I just still can't understand. So one really difficult thing is to understand torsion modules over this ring, because there's no elementary divisor theorem over this ring. So it's not a principal ideal domain. And it's very hard to understand what kind of torsion can occur here. So if you divide by p, so if you add 1 over p, so if you replace this ring by this ring 1 over p, then you have a principal ideal domain, and you understand torsion very well, but it's not local anymore. So you cannot take projective covers, and you cannot actually fix torsion phenomena. And so I don't understand how to translate between these two worlds. So the definitions the definition of these approximations you can read in a paper of mine that I put in the archive in August, but I'm not yet satisfied with it. There's too many things that I can't understand. It gives you certain representations of the algebraic group, and they all have Weil filtrations, and you can ask about the Weil multiplicities, and I do hope this gives an answer to these generations, but it's very difficult to understand these modules. Okay. Well, thank you very much. That's all I wanted to say.
Any questions or comments for Peter?
Peter, at the end, what that means is you're only focusing on the height-1 prime ideals. I mean, there could be torsion coming from things like maximal ideals. So you're ignoring that. Is that correct?
So I guess you ask how what this filtration here should actually mean.
You're talking the p torsion. If you have a module over your ring with a polynomial, it will. That's what I mean. I mean, you could have. It's going to involve things like your tau i's, which have to do with height-1 prime ideals, but it could also involve the maximal ideal of your ring. Okay, and that's not bad. That's the bad things that you were going to remove. Is that correct?
Well, at the end, if I want a tilting module, I have to remove all the torsion, and it's a kind of.
But this part, it's not something you will see in the quantum. I mean, it's. You see what I mean? I mean, it's.
I think so. That I think that's one of the big mysteries. So that, no, that's one of the points that that I actually can't answer. So there's certainly true that you see only part of the torsion in terms of the quantum group. But so for p big enough, this seems to be everything.
Well, p big enough relative to I mean
the root system actually.
Okay.
I mean, this is
so for SL3 you mean like if p is not too small. you will not find
it seems so. Oh, wait. No, actually, no, it is actually the effect because for P big enough, the Lussig's character formula says that the irreducible representations, the characters coincide with the quantum characters. And this should actually translate in the fact that you only have these tau I torsions. So it's really super mysterious, and it's this distortion part here. Oops, I'm sorry. Has a very special nature, and I just can't say at the moment how to. I mean, I just don't know how to describe it.
So can you use the Janssen sum formula, things like that, to detect that something is wrong, that you're missing something?
Well, of course, it's what I'm saying is very much connected to Janssen sum formula, but it's Janssen sums formula in this not for the quantum group over a cyclotomic field, nor over ZP, but over this ring, and I don't know if someone studied this Janssen sum formula over this ring.
What would that mean? I'm not sure what you would mean.
Yeah, exactly. I mean, so that's exactly the problem I have. That the torsion. So you have, so you don't know how to write a sum in this situation. It's a kind of multi-directional Janssen filtration that you obtain. Is it too confusing what I'm saying?
I think I follow, but I don't know. Maybe we should, go back to other questions. But that's great. I understand. What you're doing.
So there's this. I mean, I'm saying this for the benefit of others because this is a conversation that Peter and Raphael and I have had many times. But there's just this kind of repeated feature here where you have some form, and it's defined over essentially the ring that Peter's discussing. And if you assume that this form is diagonalizable, then everything follows. So you can prove Lustig conjecture, etc. And I remember, so Peter's told me this fact, Raphael's told me this fact, Ian Grodnowski's told me this fact, Henning Anderson's told me this fact. So somehow everybody notices this, gets excited, thinks they can prove it, and then realizes that you can't diagonalize this form in general. Which is somehow this, like what you're saying, this multi-directional Janssen sum formula.
Yeah, you can. I mean, you can write down these approximations. I mean, you can choose the directions you wanna look at. So these should be subsets of the. So you should choose some of these tau L's here, and then you can produce something. But yeah, it's just an approximation.
Peter, I want to make sure I understand what you've done. So I understand roughly what you do to get some sort of part of a representation of a quantum group by looking at various torsions. And then you somehow take a limit as d goes to 1 and get a representation of the actual algebraic group for the wall module filtration?
Yeah.
Okay.
Yeah.
And so, so you could, for instance, just get rid of the p-squared cyclotomic torsion and get something which was neither the first nor the second generation, but had these long legs of length 9 without the little spurs of length 3?
No, it's a little. No, it's a little. No, it's a little more subtle. I mean, let me go back to this picture. So, as Jordi remarked, this picture can be explained. I mean, this has an explanation in terms of binomial coefficients, and so the question is always which binomial coefficient is divisible by p or even by p squared or so. But it could be, for example, the binomial coefficient that is responsible for this singularity is divisible by 9, but it should still be in the first generation, and the binomial coefficient responsible to this singularity is divisible by 3, but it should be in the second generation. So there's no way that that I can see that just looking at p torsion. So in the world of the p-adic integers, not quantized, that you can give sense of these generations. You have to go to the quantum group.
But I'm asking, even in the quantum group, is there, if you do p squared cyclotomic torsion, but not p cyclotomic torsion, do you
yes.
get do you I guess I can't annotate.
Yes. So yes, you get yes. Oh, sorry, Ben. I think I misunderstood you completely. I think you're right. You get the legs of length 3 if you look at tau 1, and if you look at tau 2 torsion, you get the legs of length 9.
Right, without the little spurs.
Yes, and then if you want these, yes, if you want those, you look at 1, 2 at tau 1 or 1 at tau 2 torsion. You kill all tau 1 and tau 2 torsion. Then you get kind of everything. Get the second generation like this.
Thank you.
Very nice.
And to what extent do we know the answer for SL2? So if I give you like, tau 1, tau 3, and tau 7, do you know that you get the legs of length 3, 27, and whatever 3 to the 27 is? Whatever 3 to the 7 is?
Yeah, so, maybe 6 weeks ago, Jordi, we both had this long talk, and of course, so it's very hard to actually prove something in this tilting world, because it is. So you ask if I know that I get the right answers, right? So. And I gave this to a computer, and so far as I could calculate it, it always works. But I haven't found a proof, a mathematical proof that it could write down that would answer, that would definitely say these are the generations in SL2. But after our talk, I looked at simple representations, and there you can do something very, very similar. And there, I think it's much easier to prove that that you get the right results. I'm not done yet, but there. So for simple representations, the theory is much more manageable. When I wrote, so the paper you find on the archive in August, before I put it on the archive, I sent it to some specialists, and they were with kind of red statements that I wanted to prove. For example, I wanted to prove that the nth generation module has a filtration by n minus first generation modules, and so. Something that I thought is within reach, and these statements were all wrong, actually. there's very subtle torsion phenomena occurring. So what I propose in this article is not very easy to manage. Let me put it like this. Some of the obvious things I couldn't prove, and some of the obvious things that one would hope are actually not true. And still you couldn't define, did they have Weil multiplicity? So they all have a filtration by Weil modules, and you could hope that these characters are actually the generation characters.
So I think I need to probably ask some more basic questions. I'm trying to catch up. So in the generation philosophy, there's one, let's say, tilting character for each natural number, but you're proposing something more general than this right now. So you have cyclotomic polynomial p to the any natural number, and then you can take any collection of those. And so the more general things, like Jordi was saying, take 1, 3, and 7. That is there a way of at least like numerically generating characters of those from the well, can one extend the generation philosophy to also include these more general things?
And that's exactly what I thought. So I thought one could hope that a 1, 3, 7 approximation has a filtration by 1 approximations, 3 approximations, and 7 approximations by all subsets, and so because and I still kind of believe that on the character level that's true, but the objects definitely have no filtrations with subquotients being approximations for certain subsets. That's unfortunately that's not true. So I have to say, I mean, I can define these objects, but I cannot say much about them so far.
I see. Thank you.
Can I ask a question? I mean, is there a definition of what these various generation tilting modules or tilting character formulas are? I mean, is there a general theory like that? I'm sorry, I forget. So is it what you're referring to, or
yes? So so it started out with simple characters, and George Lustig gave a definition of this.
That I'm okay with that, but in the tilting case,
as far as I know, but I mean, Jordi knows that better. There's it's an idea that
there's no precise definition. There's no precise definition.
No definition. No.
Okay, no, that's what I wanted to check, because okay, so somehow I feel that the difficulty is maybe, to provide a good guess, maybe not yet to prove anything. I mean, somehow the difficulty is to go far enough, maybe in calculations or things like that, to be able to get a reasonable guess. I don't know.
Well, you know, there is there was this guess for SL3, this billiard conjecture.
No, yeah, but what you're trying to do is a kind of full generality approach, which is great. But you see what I mean? I mean, it's not. There's one thing is trying. What you're proposing is a way to look at things for the general case.
Yeah. But so far, I wouldn't know how this idea leads to any formula, because everything you know about these representations, like Weil's character formula, so this is not yet visible in this approach, or linkage, for example. That's,
okay, I understand what you mean. Okay, I see. Yeah, no, but there could be ways somehow to test your predictions. I mean, these kinds of questions, you could see maybe that something goes wrong using Janssen character formula, mod P, and at roots of unity. I think you could conceivably find that the predictions you make are maybe too optimistic, or you see, I don't know if you see what I mean. I mean, you would have an inequality somewhere, or I forget how it goes, but you can imagine that something, yeah, there's something like that, but maybe, I don't know.
Yeah, I wouldn't know how to. So maybe I understand not enough about this generation philosophy. So I wouldn't know what to test. If the question is, I mean, is that really, does that give an objects that whose characters satisfy this generation philosophy? I wouldn't know what to test.
I mean, one simple thing is, I guess we have no idea what the answer is in general, but we certainly can say what it should be for SL2.
Yeah. Okay. Yeah. Okay. Yeah. Okay. That's a good. Of course, that's a good remark. And as we talked about this before, and I'm working on it for SL2, but it's yeah.
I'm a bit confused. So, but at least when we did calculations in the anti-circle module, somehow from the discussions with Jordi, I always felt that in like higher rank, he would just kind of look at SL2 subgroups and kind of see the first point where kind of that is like in each of the SL2 subgroups is kind of like third generation, and then we would call this like third generation for SL3. But I mean, I don't know, like there's no.
But you would have to go, if I understood correctly, in not only in simple root directions, but in all root directions, right? To guess the characters. Is that true? I mean, yeah. And so, I mean, so this is hard to do in this kind of theory.
Any more questions for Peter? Okay, if not, let's thank him again. Thank you, Peter, for that interesting talk, and it definitely whets my appetite for more generation philosophy. I hope that Jordi or George can tell us something about it in the next semester. Let me end the recording here.